Control valves Part 2. Effective characteristics. Effective characteristics. So far, we have discussed about the ideal characteristics of a control valve. It is decided by the shape of the plug and the pressure drop across the valve is assumed to be held constant. But in practice, the control valve is installed in conjunction with other equipment such as heat exchanger, pipeline, orifice, pump, etc. The elements will have their own flow versus pressure characteristics and cause additional frictional loss in the system, and the effective characteristics of the valve will be different from the ideal characteristics. Request. It is hoped that this lecture is going to be useful to you. Please press like. Please subscribe. In order to explain the deviation, let us consider a control valve connected with a pipeline of length L in between two tanks as shown in figure 6. We consider the tanks are large enough so that the heads of the two tanks H0 and H2 can be assumed to be constant. We also assume that the ideal characteristic of the control valve is linear. From equation 1, we can write for a linear valve K1 times small a equal to K times small z, where K is a constant and Z is the stem position or lift. Equation 1, as mentioned, is same as explained in the earlier lecture, Control Valves Part 1. Now the pipeline will experience some head loss that is again dependent on the velocity of the fluid. The head loss delta HL will affect the overall flow rate Q, and equation can be rewritten as equation number 6 as shown. Delta HL is across the length of the pipeline L as shown. The head loss in meters can be calculated from the relationship given in equation 7, where F is the friction coefficient, L equal to length of the pipeline in meters, capital D inside diameter of the pipeline in meters, and V is the velocity of the flow in meters per second. Further, the velocity of the fluid can be related to the fluid flow Q in meter cube per second as shown in equation 8. Combining 7 and 8, we can write delta HL equal to as shown in the equation 9. Substituting 9 in 6 and further simplifying, one can obtain equation 10 as shown. This is the equation 10. Effective characteristics. From equation 10, it can be concluded that Q is no longer linearly proportional to stem lift jet, though the ideal characteristics of the valve is linear. This non-linearity of the characteristics is dependent on the diameter of the pipeline capital D. That is, smaller the pipe diameter, larger is the value of alpha and more is the non-linearity. The non-linearity of the effective valve characteristics can be plotted as shown in figure 7. This is the figure 7, effect of pipeline diameter on the effective flow characteristics of the control valve. So we can see that as the diameter is decreasing, the non-linearity is increasing. We begin with the linear characteristics, and as the diameter is decreasing, the non-linearity is increasing. The non-linearity introduced in the effective characteristics can be reduced by mainly point 1. Increasing the line diameter, thus reducing the head loss. Second point, increasing the pressure of the source H0. Third point, decreasing the pressure at the termination H2. The effective characteristics of the control valve shown in figure 7 are in terms of absolute flow rate. If we want to express the effective characteristics in terms of M equal to Q upon Q max, in equation 3, deviation from the ideal characteristics will also be observed. Linear valve characteristics will deviate upward as shown in figure 8. An equal percentage valve characteristic will also shift upward from its ideal characteristic, thus giving a better linear response in the actual case. Figure 8. Comparison of ideal and effective characteristics for a linear valve. So, this is the linear valve ideal characteristics, and effective characteristics has moved upwards and has become non-linear. This is M versus X graph. Thus, linear valves are recommended when pressure drop across the control valve is expected to be fairly constant. On the other hand, equal percentage valves are recommended when the pressure drop across the control valve would not be constant due to the presence of series resistance in the line. As the line loss increases, the effective characteristics of the equal percentage valve will move closer to the linear relationship in M versus X characteristics. A control valve is the final control element in a process control. Thus, the effectiveness of any control scheme depends heavily on the performance of the control valve. The proper design and fabrication of the valve is very important in order to achieve the desired performance level. Conclusion. Moreover, control valves are of different size and shapes. Only few types of control valves have been discussed here, leaving a large varieties of valves. Those are in use, to name a few: globe valves, butterfly valves, V-port valves, etc. We have discussed here the pneumatically actuated control valves, though electrically and hydraulically actuated valves are also not uncommon. The shape of a valve plug is not the only deciding factor for determining its effective flow characteristics, but other equipment connected in the line along with the control valve also affect its flow characteristics. Thus, the effective flow characteristics of a linear valve may become non-linear, as has been shown in this lesson. For this reason, equal percentage valves are preferred in many cases, since their effective characteristics tend to be linear in presence of head loss in the pipeline. There are distinct guidelines for selecting the valve size and shape depending on load change, pipeline diameter, etc. Bypass lines are also sometimes used with the control valve in order to change the flow characteristics of the valve. Request. It is hoped that this lecture is useful to you. Please press like. Please subscribe.